phone number. Okay, now let me start with a review and maybe just a comments for this week lecture. So the lecture will be using the same link, the same WebEx link. So today's lecture and Thursday lecture also we are going to use the WebEx, and I think it's quite smooth now. So I hope uh, it doesn't uh, reduce our discussion because it's online. And if we finish like this week lectures, then perhaps next week we are going to have offline class if there is no other case, I think, and hopefully we can go back to class. Okay. So just a review. What we have done last week is we have the curvature, right? The curvature, and then the tangent, the unit tangent, the unit normal, and binormal, and all these essentials. I think this is all important for the chapter 13. So I hope you're already familiar with the unit tangent. Okay, it's related to the r prime. Okay, and the normal is related to the unit tangent first derivative t prime, and binormal is the product of a cross product of t and n. So uh, from the notions uh, of the equations, you see that it has the first derivative. And this shows us that it should have been some orthogonality, right? Some orthogonality. So we will see that the r prime is orthogonal to the tangent, and the t prime is orthogonal as well. And this binormal is orthogonal to t and n, and we can draw the tangent in this diagram. So this three-axis diagram. Okay. Okay, and then we are going to look at what the torsion means. So we have the osculating plane here, osculating, and this is the normal plane. And from these two, we can imagine, and if we take derivative with respect to s, this part, this is telling us how the normal plane changes as the point moves along the curve. Okay, so when the point moves, along the curve, then the tangent, they will rotate. Okay, so if you look at the tangent, let me draw here. The tangent maybe first is here, and then if we move, tangent is going here, and if you move here, tangent going here. So tangent will be moved, and it's having or it's facing the directions of n. So it's facing here, for example, facing here, facing here, and then from there we are informed that the osculating plane also changed. Aside from the normal plane, the osculating plane also changed because all these three axes will be they are moving together, right? So when we are having the change with respect to S for this binormal, actually we are going to prove that these directions and this B, this direction of this arrow will be parallel to the N. So actually this should be written that this factor should be parallel with the N, and because of that they have the parallel property, then we can take it into equations and make a new definition that is a torsion that has a scalar value in which they will relate the dB over ds and n. Okay, and we can rewrite this and multiply both sides with dot n, and thus we are getting the formulations for torsion. Okay. Okay. Now, if we are writing the torsions in terms of this formulation, perhaps this is not really or it's not easy for calculation, because dB over ds is not something that computerized or easy to calculate, easy to compute. We are going to use chain rule and state all with respect to dt. And I think this will be more intuitively will be more correct. So we can write the dv over dt and dv over ds and ds over dt. We can rewrite the dv over ds as dv over dt divided by ds over dt. And thus this will result in, this will be p prime t, the first derivative of the binormal, and the ds over dt is the value of the r prime. And because of this, we can write the torsion as a function of t, and then we can change dv over ds, becomes dt divided by r prime t, and multiply with the dot product and t. Okay. So what's the implication of torsions? Implication of torsions, if I check the drawing, let's say we have the circle on this xy plane, circle 1 1, so x squared plus y squared equal 1, and based on calculations we can think it has a constant curvature of 1, and then there's no torsion, so we can say the torsion is 0, so because it's stay as it is. But if we take as the curvature half and the torsion half of this helix, we are going to have some bending. Okay, so it will go through here, go through here, go through here. So this curvature will be on bends the curve, and this torsion will be twisting upwards. And because it both value has a constant value, which means that in every unit, in every distance, it should be equal. Yeah, the two thing is equal. It's relatively constant. But if this is a function, then it will be have it will be vary the twisting. It's not a function. Okay. And we can also rewrite the torsion if we correlate the r prime, r double prime, and r triple prime. So we are having the third derivative. We can take this and write down the cross product, then dot the triple derivative, then divide by okay. There are several ways to prove this, but I think I will not have much time to explain. But this form eventually not really that particularly used. For some cases, we can observe and analyze through this torsion formula, but most of the case we are going to have the first one here. This one is most likely to be analyzed because it's more about binormal, normal, and r prime. But this should be equivalent, should be equal with it. Okay, so this torsion, the section about torsions will end 13.3. And we will skip the 13.4 because I think this is more likely to be physics, and all the essentials we already taught in 13.3, and we can apply to many subjects. Okay, wait for a moment. Okay. Let's continue. Now the next part on our lecture for today's class will be on chapter 14. So chapter 14, I hope everyone watched the additional video that I mentioned in the Moodle. If not, you can watch later on. It's only the how to say the introductions on the partial derivatives, function of several variables. Okay. So we will start the chapter 14 from 14.2. Okay. We are starting with the limit of functions of two variables. Now, in previous calculus, mostly the calculus 1, we are dealing with single variable. In calculus 2, we will deal with multi-variable. So instead of f of x, we are going to denote the functions into several variables. For example, two variables x, y, or perhaps three variables x, y, and z. Now to start with this chapter 14, the partial derivative, we are going to start with the limit. So if we are going to have a functions of two variables, if we compare, let's say we have sine x squared plus y squared, square root of y squared, and then other function, be different function, g. Okay. Now, if we have x and y both approach 0, 0, or we can say it's approaching the origin. Now, what should be evaluated within these two functions? Now, first, we can take this and let me check. Okay, maybe we can take it into some values. So if you check with some values of x, y, if you check one by one, using some numbers that closer to 0, 0.2, or maybe start from negative 0.2, then negative 0.3, 0.3. So we start to look on, maybe just take it. And take several other numbers. The first one, let me write this is 1 and 2. The first one, this will go to 1, and the second one, this will go to doesn't exist. Or we can write down that the limit this is from formulations from the table. If you check using some several numbers, and you can make some conclusions from there that this is equal 1, and the other one here, and the other one this doesn't exist. Okay. Now before we looking into more analysis, let me go start by definition. First definition. In general, we are using the limit to state our result FL as usual, I think. And let f be a function of two variables whose domain D includes points arbitrarily, or you can say just close to the point AB that we want to approach. Then we can write and say the limit of x and y as x and y approaching AB is L. Okay. And we can add if for every number epsilon that is positive, there is delta that is also positive, such that if xy is on the domain and the distance between those two with from xy to AB, we can write in this distance formula, is less than delta, then the distance between these two is less than epsilon. So again, epsilon delta is pretty much how to say, it's a little bit abstract at first, but it's actually visualize how small. So epsilon and delta visualize how small it is, how small the gap is. And in calculus 1, we are only focused on the 2 dimensions. We're just looking at there's a gap, okay, when you have the x and the delta, and then f of x with the y-axis, the limit number, right, the L, and we can easily connect those two. And here it's a little bit tricky, and we need to imagine. Okay, so if we have f of x, y, instead of we have having a line or a length, we are having an area. So if we draw, let me input the drawing. So if we draw and imagine, let me start with this. If we look on the area from the top side, we see the domain. We see the domain. The domain is within the area. So all x, y. Okay. And inside is having the point AB. Okay. And the xy will be from the area that nearby AB. Okay. Now if we translate this, okay, with a function, with function f, it will go through our number L, and of course nearby that L we have some L with epsilon, with the distance epsilon. Okay. So now the delta is the radius of the circle. Okay. And this radius can be observed with the distance. Okay. And if we look on more 3 dimensions, we take from isometric view, we see from here that's actually this area is this one. Okay. Oh, sorry, this one. So it's projecting through here. So actually this one is the surface that is projecting to xy plane. So as we can see, This is the circle, the domain delta. So it's a small domain, so it's the domain total domain may be here. So we are just focusing on the small domain and taking some point, and we can simulate where the L and the epsilon. Okay. Okay. This is just definitions with precise definition. Okay. To show that we have those epsilon and delta that is really small. And still, we need to answer how to prove this part, okay, that this doesn't exist. Okay. So instead of using the table numbers, how to prove that this limit is not exist. So to show limit doesn't exist, we need to take on a definition, or perhaps a picture, okay, how to make it. So first, if we imagine this AB, or maybe start with from here, AB. Let me erase this. If we want to approach AB from this XY, it can be from anywhere, right? It can be from anywhere. It can be from anywhere. So this graph or this picture showing you that we can go from here as long as it's within the domain. We can go from here, we can go from here, we can go from here. So we can say we have different paths to approach AB. Okay. Now, the definition for this limit, whenever you take some path and you compare with another path, the result, if you want the limit to be exist, the result should be the same. If not the same, then the limit doesn't exist. So let me write the definition first, and then we can see a more analytical result. So if functions of xy going to, let's say, L1, so a number L1, as xy approach AB along path C1. Okay. So path can be any line. Okay. It can be line equations, linear, and anything. And if f of xy goes to L2 as xy approach AB along path C2. So we have different path. Okay, different path. And L1 is not equal L2. So it's different result. Different result. You can say then, because this is different, then limit doesn't exist. Okay. Now, if you still feel a little bit confused, let's take some time to remember our definition of limit in calculus 1. Okay. In calculus 1, if you remember, let me draw a random function. if we have let's say we have L for this A, and then the limit, okay, if we take the limit as x approaching A from the right, of x, this will be equal to limit from the left, it should be equal L, then limit exists, right? You can write a definition like that. Now compare with what we have in a function of two variables. It's actually similar. But how we can approach this left and right is from this path. Okay, so for example, have this. Okay, I want to approach AB here alongside this. Maybe this is when x equal maybe 3. Or we can approach this AB when y is equal maybe 4. So if we compare, so when we compare these two, we make one variable a fixed constant, and then we take the substitutions and evaluate the limit and see the result, whether it's equal or not. If it is equal, then we have the limit. If it's not, then the limit doesn't exist. Okay, now go back through our questions is limit as x, y approach 0, 0. X squared minus y squared, and then x squared plus y squared. Now we have this. Now first, approach x, y, approach 0, 0 along x-axis. Means that y is equal 0. So the functions become fx0. Or we can write this as x squared over x squared equal 1. So we will have xy going to be approaching 1 as xy approaching 0, 0 along x-axis. And then we can also check along y-axis when x is equal to 0. So we have f0y, and this will be -1. So f of xy, this will be approaching -1 as xy going to 0, 0 along y-axis. Okay, so because L1 is not equal to L2 as we mentioned, f has two different limits as xy approaching 0, 0. As a conclusion, this confirms that limit doesn't exist. Okay, and the curve y equals 0, x equals 0 is a typical curve that is easiest to be concluded. So whenever you have like 0, 0 like this, perhaps you need to change one side of point with 0 and check the result. The other curve that usually easy to be observed is y equal x. So if you check along y equal x, it's also easy to be evaluated. Okay. Okay, do you think we need to have a break or no? I think we can just continue, right? But maybe slowly. Do you think so? Okay, because I think because we we are using this online class, so it doesn't really bother you for having a break or not. And we will have, I think, we finish maybe early. That's also okay for me. Okay, perhaps any questions? Okay. So far, the screen also fine, right? There's nothing trouble with your viewing when you see the screen. I think okay, right? I hope it's okay. Okay, good. Thank you. Okay, so first, let me just repeat what we have done. First, taking limit for function of two variables is we are taking, like for example, this point we can have from any way, right? But the easiest one is we can just take it with line equation, maybe here and here. So this is x equal a, y equal b. So we are making x and y each as a constant, and then evaluate the limit, and we have found the result, and perhaps that is the confirmation that okay, we have the limit, right? So, and the other one using this y equal x. This is another one that typically we can also check. So we can check this three line for the path, so that this is how we can approach the point A, B. Because we now approaching not in a line. Usually we are approaching in a curve, right? Like here. We are approaching along the curve itself. Okay. But now we have an area, so we have a quite large area that we can cover. So we need to think more. Okay. So we can use several line equations, or maybe curve that is maybe parabolic curve. If that is also, we can prove that uh, we can connect the point to that parabola. It's also okay. But then let's just take into another example to give you more understanding. Okay, now the other part is, let's say we have a function, and if take limit as 0, 0, it's asking exists or not. Now, if we are doing this, the first thing we can do is, because it's going to have the origin 0, 0, so we can use the x equals 0 or y equals 0 as our path. So we can take it into our calculation. So we are going to have, if start with y equals 0, so we'll have f x 0, and we'll have x, and then 0, and then x squared, and then 0. And thus this will be resulting 0. So this is as xy approach 0, 0 along x-axis. And if we are using the other equation, x equals 0, it's also 0. Okay. But if we get this result, do not confirm or do not conclude it exists. We can try the third one that I told you before, the y equal x. So we can make it into our f x x. So if we exchange y with x, so we'll have half. So as along y equal x. So the given limit, because we have different results, so the given limit doesn't exist. If you see curve, yeah, this is the function of two variables. Okay. So if we look on y equal x, perhaps y equal x is at this line, right? If you see how it looks when it's approaching 0, it has some curvy structure, right? So that's why it doesn't exist, because it has different results. So when we have approaching 0, it's going to be uh, 1 over 2. Okay. Now let me go through another different function. Still approaching 0, 0. Okay. We need to check whether it exists or not. Okay, it has similar structure if you put 0, right? If you put 0 for each case, for y equals 0 and x equals 0, it's going to be 0 for that matter. We can let a line equation with slope m, okay, and then we can take this as our approach. We can simplify it. But from here, for any line equations that we have, if we take this to 0, then this is also going to be 0, as xy going to be 0, 0 along y equal mx. This is another way to check using y equal mx. But if we check with the parabola, with the quadratic equations, or maybe x equal y squared, yeah, because y4, y, yeah. Let's say we have the parabola x equal y squared. We will have this will be 1 over 2. And again, because fxy going to be 1 over 2 as xy going to 0, 0 along x equal y squared, then limit doesn't exist. Okay. If there's no question, we can continue. If you want to ask or maybe feel confused or want to review something from previous slides, let me know. Okay. Okay, the next sections, after we deal with the limit, similar with what we have in calculus 1, we're also going to have the continuity. Wait for a moment. Okay, sorry for the continuity. Okay, let me write here. We remember in calculus 1 that the continuity, when we have a limit, if we know the limit exists, then it will be continue when it's equal with in that exact point, right? So of course, if you have like a hole, this will be discontinue, right? So it should be perfect without any uh, uh, any defect on in between the line. Okay, so a function of two variables is called continuous at a b if limit perfectly the same. This is similar. Okay, so we say that f is continuous on domain if f is continuous or at every point AB in C. This is continue. Okay. If we bring up our limit, not limit, but the function, the same function as before, x squared minus y squared plus y squared. If we imagine at 0, 0, the functions will not be defined, right? The function f x y is discontinuous at 0, 0 because it is not defined. So the domain okay. But we can also make a piecewise function if you would like to make the definition of continued becomes more defined. We can let this becomes two definitions. So it could be 0 if xy is not 0, 0, if xy equal 0, 0. So with this, because of the addition of this piecewise, then G is defined at 0, 0. But the problem is limit still doesn't exist. Okay. So still not continuing. Now we have another one. Let's make it another piecewise. We can check using limit along parabola. It's two parabola. So aside from x0, y0, we check the other two parabola. And I believe that the result will be similar. That is 0. So we are going to have limit equal to 0. So it's equals 0 and the limit also equals 0, and we can say that therefore f is continuous at 0, 0. And so it continues on the real numbers and in the surface. Okay. Okay, let me continue. If we have a composite function, if the f is a continuous function of two variables, and g is a continuous function of single variable, that is defined on range of L. So we have, then we have H equal defined by so H is also continuous function. Okay, so this will be in a composite structure. Okay. Now, how about if we have more than two variables? So functions of three or more variables. So we can write the limit x, y, z approaching a, b, c, x, y, z equal to L. And we have the distance between x, y, z, and a, b, c is given by using the distance formula or using Pythagorean. Okay, so from here we can write a precise definition for the three variables. So if x, y, z is in domain of F, and the distance in a delta value, then we have an epsilon, which has a distance from the functions to L, and function f will be continuous at ABC if the limit is equal when you assign the point inside the function. Okay. So if we have more than 3 variables, we still can, at least from the definitions, we can make out the definitions, that is, if f is defined on a subset domain of any real number in any space, so this x is not actually x. Let me make it into more bold. It's different x, just to note that it can be x, xy, xyz, xyz, w. Okay. So it means that for every epsilon that is positive, there is a delta such that this x is not x as in a single variable, it's different x. So I'm making the x seems bold because it's different. So if n equal 1, then this bold x will be equal to x. And this a should be also bold. Sorry. A is equal a. And if n equal 2, this x becoming x, y, and A is AB. It's a factor notation. So we can make this, or maybe if you want to write in your notes, aside from making bolts, maybe making it to arrow. And we have n equal 3. This will be having x, y, z. A, B, C. Okay. Okay. Now let me continue. Okay, I'll continue. So the limit and continuity finish. Next part is we have 14.3, that is our core section, principle. This will be the partial derivative. If you read the textbook, I think it seems to be a little bit too much word to see, but I would just want to emphasize which one is I think the basis one. Okay, let me write first as if f is a function of two variables. Suppose we let on the x vary while keeping y fixed, like we did in the limit before, right? We have a path, right? We have a path. We take one variable to be dependent, we can change, and the other variable will become a constant. Okay, so if we take this in our approach, then we consider a single variable function. G of x that is equal to xb. B is when when y is fixed with line along y equal b. And if g has a derivative at A, then we are calling this as partial derivative of the function f with respect to x at AB. Okay, so based on what we have understand from the limit before, partial means we are deriving the functions that has two variables, but we are derive with respect to each of the variables. So first, for example, here we are going to derive with respect to x. We can write f x like this. This means partial derivative of f with respect to x at AB, and simply we can write down this equal to g prime a, where g of x is equal to f x b. And of course, from here, the g prime a as in limit definition. So we have fx ab equal limit. This is f a plus h b minus f a b defined by h. And similarly, we'll have fy. So this is when x is fixed and y will be a variable. So we will get limit and this will be the definition of partial derivative of each x and y. And this should be provided that limit of these two limits exists. Okay. And notations, the notations that we can write. There are several notations that we can use, and it's up to you. You can pick which one you prefer. For example, the partial x, let me say partial x as partial derivative of f at x. Okay, so partial x, you can just write fx like that, or dou f dou x with Leibniz notation, or dou x f xy, or z dou x, and or f1 or d1f or dx f. Oh, by the way, we can write f of x y as c. Because every assignment of x and y will result in different in the z-axis, right? If we change the height, the contour, you see my additional video 14.1. And the other one, same, but using y. So the same. Okay. And how we can use this partial? let me just give you an example, and I think if you understand how and familiar with it, I think you'll be fine for the calculation part. So if we have, but if you're still not really sure how to do it, please pay attention. If you have fxy 3x minus x squared y squared plus 2x cubed y. If we are going to take the partial derivative with respect to x, then we are going to write fx like that. So what we are going to do now, we are going to have 3 minus 2x y squared plus 6x squared y. So what's happened here? So what's happened here is we are going to treat y as a constant. So just leave as it is. So treat y as constant. Okay. We take the partial y. 3x is a constant, then it will be 0. Okay. And then this will be minus 2x squared y. And then plus 2x cubed. And then y become 1. So this is treat x as constant. Okay, I hope everyone clear for this point. Do you have any question for this part of partial? So in practical, it's actually not really complicated, but it should be, if you remember how we are approaching the limit, it should be having a connection. If you remember how we can approach the point A, B from different paths, right? And the one that is applicable and easy to be followed as is when we have or we can treat the other x or y as a constant, and we can have a derivative with respect of these two variables. Okay. If there's no question, I think we can still have 10 or 15 minutes left. So let me continue. Okay, what happens if we have f of x as x e x squared y? Evaluate example partial x and partial y at 1 and n ln 2. Okay, you can try for a couple of minutes, especially if you still not able to do the partial derivatives. Okay. Please take your time to evaluate. But I think if you already familiar, I think it's still okay if you want to check your ability to derive this function. Okay. Now, if we take partial x Then we are going to see that we have x and this part. Okay, so we have two functions. So we are going to have a product rule. So first, we have a product rule that is e to the power of x squared y, and then plus we'll have 2x squared. So 2x squared y, and then e x squared y. And a partial y. Partial y is easy. We treat x as a constant, so x is just as it is, and then e with power of x squared y, so it will be x squared. So x squared multiplied with x will become x cubed, and we have e with power of x squared y. Okay, and evaluate both at 1 and ln2. So this is supposed to be equal to e with power of ln2 plus 2 ln2 e ln2, or this will be 2 plus 4, right? This will be 2, so 4 ln2, and this should be equal to e with ln2, or this is equal to 2. Okay. Okay, another example. Let me go through another example. Sine x over 1 plus 1. Question is partial x and partial 1. Okay. Okay. Try your best to evaluate. Okay, if you see the structure, it has sine, and all the functions or the variables both are inside the sine. So whatever you are doing, then the idea is to derive the sine. So you should be having a cosine, and the trouble will be having inside the chain rule inside. So we will have sine will be cosine. Okay, let me write one by one. X 1 plus y, and then you should continue with the chain rule for x and 1 plus y like that, and this should be equal, and since when we are dealing with the partial x, then we are treating y as a constant, right? So y as a constant, so this is a constant. So the derivative of 1, derivative of x is 1, so it should be 1 over 1 plus 1. Okay, I hope it's clear. Now partial y, we treat x as a constant, but still at the very first step it should be equal, right? The difference is the next step. So x is constant, still x. So we write cos, cosine, and then this is x, and then 1 over 1 plus y. The derivative of 1 over 1 plus y, this will be equal to -1, right? So we can write this as negative at the front and divide by 1 plus y squared. Okay, I hope this is clear. Okay, I hope the points are clear for today, and hopefully we can go back in class next week. But for Thursday, remember we still have an online class and still the same WebEx link. Okay. So is there any questions? If there's no questions, yeah, at the end. Okay. If there's no questions, then we will finish our class. Okay. So thank you for joining the online class for today, and I will upload the recording to the Moodle. If you want to review, you can watch on the Moodle. Okay. Let me go through the. Okay. If you need the QR code. Okay. If you're done, you can leave the meeting, and see you next Thursday.